So welcome everybody again. Right now we will have Tetsu Toyoda from Kogakuin, and he's going to talk about the 4-point condition and subsets of K spaces.
Okay. First of all, I would like to thank the organizer for inviting me this wonderful workshop. I'm very happy to be here. So I would like to start by drawing some pictures. Okay. This is the class of complete Riemannian manifolds. And this is its subclass consisting of all simply connected manifolds with non-positive sectional curvature. And I would like to consider a broader class. Geodesic. This is class of geodesic metric spaces. And the class of cat0 spaces is defined as a subclass of this broader class, and it's natural generalization of this subclass of Riemannian manifolds, so cat0. So a metric space is cat0 if and only if it is geodesic, and every geodesic triangle is not fatter than its comparison triangle in Euclidean plane. Okay, so in this talk, I'd like to consider an even broader class. This is the class of all metric spaces. Natural question here is, what is a generalization of cat0 in this broader class? Okay, and there are many answers, I think, but one natural answer to this question is class of spaces that admit distance preserving embedding into a cat0 space. Okay, and we write like this. If X is in this class. Okay. And there is a fundamental problem, open problem concerning this class. Problem posed by Gromov. Characterize those metric space X that admit distance preserving embedding into cat0 space. So to get a better feeling for this problem, let us recall the theorem proved by Lev. Life. Okay, is this okay? Life. Yeah. So they prove that X is cat0. I mean, a metric space X is cat0 if and only if it is geodesic and any 4 points in that space satisfy this inequality: y squared, yz squared, dx zw squared plus dx wx squared minus dx xc squared minus dx yw squared greater than equals to 0. Okay, so I think most of you probably know about this fact. There are many names. This inequality has many names, but in this talk, we say X satisfies short diagonal inequality if this holds. Okay. Okay. So this second condition, I mean short diagonal inequality, is a condition for general metric space. So I mean it makes sense without assuming the space is geodesic. So you can consider the class of general metric spaces which satisfies this condition. Okay, and Berg-Nikolaev theorem says that class is a generalization, one generalization of Cat0 space. I don't know, like this. Okay, so we can now ask a question that does this class and this class coincide? If it's the same class, it would be an answer to the Gromov's question. But actually, the answer is no. These classes are different. To see why the answer is no, we recall the following theorem. To the best of my knowledge, this was proved Gromov and maybe Ostrom independently. Okay. They proved X is Cat0. Then metric space X satisfies following family of inequalities. That family was indexed by these parameters. A little complicated, but squared minus t s dx yz squared plus s t dx z w squared plus t 1 minus s dx wx squared minus s1 minus s dx xz squared minus t1 minus t dx yw squared greater equals to 0. So it is easily seen that this, okay, I have to give this inequality some name. We say X satisfies box times inequalities. This form. This nice symbol is based on Gromov's notation. Okay, and it is easily seen that short diagonal inequality is a special case of this inequality. If you take this parameter for S and T, then you can get a short diagonal inequality. So this is a special case of this. And it is also easily seen that short diagonal inequality does not implies this. So you can construct actually 4-point metric space that satisfies this inequality, but does not satisfy this inequality for some parameters S and T. So because box times is necessarily condition for distance preserving embeddability into Cat0 space. So this says short diagonal inequality is not enough to characterize this class. Okay, so there is some example here. Okay, so the problem here is how about box times? So this theorem says, so there the class which satisfies box times inequality is class like this. So how about box times? Does this characterize distance preserving embeddability into Tetsu space? Actually, okay. When Gromov introduced box times inequality, he already stated that for a metric space at most 4 points, this is x. Okay, maybe I have to write x satisfies if and only if distance preserving embeddability. Okay, so at most, so 4-point metric space, it characterizes distance preserving embeddability. But actually, we know that box times is still not enough to characterize this class because we have very nice example constructed by Nina Lebedeva. She proves that there exists 6-point, maybe I have to write 6-point metric space X such that X satisfies box times, but does not admit distance embedded into Tetsu space. So box times is still not enough. So here is my main question of this talk. How different the conditions are box times and distance preserving embeddability into Tetsu are. I think this question is interesting for at least 2 reasons. One is that it may be a first step to tackle Gromov's problem. So to tackle Gromov's question, you have to find a property of subsets of Tetsu spaces that does not follow from box times inequality. So answering this question may help you to look for such properties. And another reason is that the space with box times, which is a generalization of Cat0 in general metric space, should be interesting in its own right. Okay, so I want to answer this question. So to answer this question, I have to measure the difference between these conditions in some way. So in the rest of my talk, I'd like to explain one method to measure a difference between these conditions. And using that method, I want to explain idea of the proof of myself. Actually, this is the goal of this talk. So if X is a 5-point metric space, then X works. Okay. If and only if Okay, this is the goal of this talk. And maybe looking at this result, you might wonder what's so interesting about a result about metric space, just 5-point metric space. But when I discovered this, I was really surprised because to tackle Gromov's problem, thanks to this Gromov's theorem, every properties of 4-point subsets of Katsura space spaces follow from box times. So you have to start by looking for the properties of 5-point metrics, 5-point subsets of Katsura spaces, which does not follow from box time. So, but this theorem says box times imply all properties of 5-point subsets of Katsura space. So you can start your adventure by looking for properties of 6-point subsets. So it's a little surprising for me. Okay. So, okay. To explain how to measure the differences between these conditions, first, I would like to recall some notions introduced by Gromov. Okay. Let n be an integer like this, and let this is a cycle graph. Okay, and cycle graph is vertex set En and edge set En. Definition. Gromov. He defined that X is cycle and copper. Here, copper is an arbitrary real number. So far, I talked only about cat zero space, but here, copper is an arbitrary real number. If you don't like this, you can always assume this copper is 0. It's okay. Definition. For any map from vertex set with cycle to your metric space X with additional condition. V, Vn, Vx, Fu, Fv, most the copper. This is diameter of model surface. So if you consider non-positive copper, this additional condition is nothing. Okay. There exists a map, a comparison map to model surface such that the copper Gu, Gb, dx, Fu, Fv, if U and V, it's a vertex of a cycle, are joined by an edge. And opposite equality if UV, En. Okay, here I think it's better to draw some pictures about this definition. Okay. Do this.
Can I see the definition again while it is there?
Let me draw a picture for the case.
I want to see the
fine.
definition once again.
So this definition says for arbitrary map, this means in X, so you take arbitrary arrangement of 5 vertices of the cycle graph, like this, and you can take appropriate arrangement in model surface such that with shorter edge length and with a larger diagonal length. Okay, this is the meaning of this definition. Okay, and I want to record one more notion introduced by Gromov. Gromov defines X is WIRN if and only if any map and any J. It's a little complicated, but so we have some inequality. Oh, sorry. I plus 1. It's a kind of generalization of short diagonal inequality. Sorry, I have minus. Okay, equals 0. So it's a generalization of short diagonal inequality, but maybe looking this inequality, maybe it's difficult, maybe it's not so easy to understand, fully understand the meaning of this inequality, but it's okay for purpose of my talk. Okay. So what is important for purpose of this talk is this. Okay, maybe I have to erase this one first. Important for our purpose is this. We prove that X is cat kappa if and only if X is the kappa geodesic. It means that any 2 points within distance d kappa can joined by geodesic and cycle 4 kappa. So cycle 4 is most important, I think. And for kappa equals 0, cycle 4 0 is actually equivalent to box times. Okay. So and finally, distance preserving embeddability implies cycle n 0, and this implies n for any n. Okay, so for our purpose, I mean, measuring these conditions, measuring difference between these conditions, it's a natural question to ask. I think this is not true because there is linear derivatives example, so it is not true. But we can ask, how about these implications holds or not? Actually, when Gromov introduced all these concepts, he already think about it. Okay. 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 For about this question, Gromov expressed somewhat negative opinion. Gromov's remark. He stated that we shall see later on that cycle 4 implies cycle cycle K for all K 4 in geodesic case. But this is apparently not so in general. So he stated like this. And for the next question, second question, actually, he posed this question as explicitly as an open question, Gromov's question. There are many Gromov's questions. This is one of his questions. Cycle 4 Z. Oh, sorry. It's okay. There implies UN for any. And this is question. Okay, so actually, we already have answers to both of these questions. Maybe I come here. Okay, so first answer to the second question. Kondo, myself, and Rehara. Sorry. N. Okay, so we answer his question affirmatively. Okay. And for first question, actually, this also falls through for N. Okay. Before proceeding any further, I want to, for advertisement, I want to explain a little about idea of the proof of this theorem too. Okay. So actually, I proved a slightly stronger statement. Theorem 2 is a corollary of the following theorem. So if X is cycle for copper, then for any n and any map, this is the vertex set of the cycle, of n cycle. For X with additional condition, X Fu Fb is copper. There exists a map from to copper such that Dn to copper Gu Gb. Actually, we have equality here. X Fu Fb F UV En, and this inequality if UV is this, and one more additional condition, and GB, this is comparison map. En forms vertices of a convex polygon in model surface. Okay, this is what I proved, and theorem 2 becomes a corollary of this result. Okay, and maybe if you know Leschetizky majorization theorem, this theorem can be seen as a generalization of Leschetizky, maybe it's better to say analog of Leschetizky majorization theorem for cycle 4 space. And actually, I have to write argument of Ballman in his lecture note to prove Leschetizky majorization theorem works to prove this, work very well to prove this. So actually, when I wrote my preprint, I didn't know that this idea to prove Leschetizky majorization theorem due to Ballman. So I didn't mention it in my preprint. It's my fault. So now I'm preparing revised version. So in it, I have to mention. Okay. So this is a little advertisement. So I proceed further. Okay. Okay. So now I have explained that these necessary conditions for distance preserving embeddability into capsule space follow from box times. So maybe we can say that box times is not so different from distance preserving embeddability, but just maybe. So to measure the difference between these conditions, I would like to generalize conditions. There are two types of condition. One is inequality condition like box times and short diagonal inequality. And another is graph comparison condition like cycle condition. So we want to generalize both of these conditions. First, I generalize a condition for inequalities. Maybe I have to write Andoni Naho name. Okay. Light. This is a set like this, and this is family of real number indexed by 2-point subsets. This means 2-point subsets of this set. Oh, I mean the set of all 2-point subsets. Okay. We say X is some metric space satisfies Aij quadratic metric inequality if any or n points in X satisfies inequality like this. Dx, xi, xj, and of course here ij is here. So, okay, so it's just notation. But, Andoni, Naoho, and Neiman I defined this type, use the word quadratic metric inequality, a little bit different form. Okay, and I define one more thing. Aij quadratic metric inequality is a cat-zero quadratic metric inequality if and only if every cat-zero satisfies it. Okay, so we define some general inequality or metric spaces like this, and we say that inequality is cat-zero if every cat-zero space satisfies this inequality. So for example, box times is an example of cat-zero quadratic metric inequality. So many cat-zero quadratic metric inequalities are known. Okay, so next, I want to generalize graph comparison property. I don't know. It's okay. Okay. Okay, I define, okay. HE be an arbitrary graph. And we say metric space is G0 if and only if or any f from, but except to your metric space X, there exists a cat-zero space. And map to cat-zero such that dx fu fb fub line e and opposite one if okay. So I replaced a cycle graph in definition of cycle condition with general graph. And I also, for some technical reason, I replace the model surface in definition of cycle condition with some Cat0 space. Okay, so then it easily seen that these conditions are necessary condition for distance preserving embeddability into Cat0 space or any graph G. Okay, it's easily seen. So if X is Cat0, then you can take a map G as map G F itself. So you can take F itself. So it easily seems that this necessary condition for distance preserving embeddability. So now I define a lot of conditions. A problem here is there are many necessary conditions for distance preserving embeddability into Cat0 space. But no matter how many necessary conditions you gathered, it's still a necessary condition. So it's a problem. But I have the following fact about this problem. Okay. Which one? I don't know. Maybe this one. I don't know. This one maybe. Anthony, Naho, Neiman is that if for any point metric space, then our X-admit distance preserving embeddability into Cat0, if and only if X satisfies all Cat0 quadratic metric inequalities on endpoints. Okay, so this means that you gather all Cat0 quadratic metric inequalities, then you obtain sufficient condition for distance preserving embeddability. It's a direct consequence of the fact that a square of distance between endpoints in Cat0 space form closed convex cone. And so it's a direct consequence of that fact. But I learned this fact in their paper. Okay. So, but we still have a problem here. What is the problem? Problem here is what is all Cat0 quadratic metric inequalities? So many Cat0 quadratic inequalities are known already, but I think nobody knows all Cat0 quadratic metric inequalities. So that is problem. So to overcome this problem, I translate this theorem in terms of graph comparison. Maybe. Actually, this is a key lemma. If X is an point metric space, X against distance preserving embedding into Cat0, if and only if X satisfies X, maybe X is G0 for all vertex graphs.
So sorry, can I ask a question?
So I translate this. So now I think there are many n-vertex graphs. There's still many n-vertex graphs.
I think Vitaly has a question.
Okay,
Vitaly?
okay.
Yes. Can you hear me?
Yeah.
Can you hear me?
We cannot hear you, Vitaly.
Sorry, can you hear me?
Yeah, we cannot.
I cannot hear.
Well, I cannot.
Sir, actually, we can hear you. We can hear you, but somehow they can't hear you. That's the problem.
So people on Zoom can hear me, but not in the room. Well, that means that something is there somebody from Fields that can maybe fix it?
Shane is looking at the problem, Vitaly. So please wait.
Okay.
Can you unmute yourself and ask again?
Okay, can you hear me now?
No, we cannot hear you.
Okay, then maybe I'm.
Yeah, write it in the chat, please.
Maybe.
It's okay. I think it's a never mind. Okay. So I proceed. Okay. Okay, so I'm waiting his question. I use this time to sketch a proof of this lemma. Okay. So thanks to Andoni Nao-Neumann's theorem, what I have to prove, what I have to show is any cat-zero quadratic metric inequality are satisfied if this condition holds. If this condition holds. So we have to prove this side. So I mean, take this is an arbitrary, coefficient of arbitrary cat-zero quadratic metric inequality. You can construct a graph from this coefficients. So we can define vertex set is this, and edge set is like this, ij, aij, positive, and define graph like this. And then, because x satisfies G0 condition, we have for any endpoint x, there exists a cat-zero space and endpoints in cat-zero such that dy, this is y, yi, yj, dx, xi, xj, if aij positive and opposite 1, if aij negative. So it's easily seen that therefore we have aij this inequality holds because y is cat-zero. And this is a coefficient of cat-zero quadratic equality. And we can divide the sum and how to write aij dx yi yj squared minus it's negative I have to write y here. Yj, and thanks to this inequality, we have just the same, and we change here. Dx, xi, xj, and I don't have any space here, but combining this, is equal. So an arbitrary Tetsu quadratic metric inequality holds on this space. So finally, okay, okay. So by using this key lemma, we can show box times implies box time it's equivalent to cycle 40 implies G0 for many graphs. Many, including all 5 vertex graphs G. So which proves seven one. Okay. And finally, I have to remark one more thing. Oh, oops. It's okay, I don't know, but remark, there is another proof. Another proof of theorem 1 was obtained by Nina Lubelba and Anton Petruni. And in my argument, I did not construct an actual embedding, but their proof constructed actual embedding into Tetsu space in very nice ways. So I really recommend you to check their argument. It's very interesting results. So, okay, so this is the end of my talk. Well, thank you for your attention.
Thank you very much for your talk. Are there any questions?